Hello! In this screencast, we will be reviewing some material science test solving strategies for electronic properties. All of the test examples provided in this screencast came from a fall 2012 material science course at Arizona State University. To begin the screencast, we have a summary of electronic properties concepts, followed by multiple choice test example concept problems. Then we will dive into calculation test example problems, and we will end with some band structure schematic test example problems. To skip to a particular section, just click one of the links provided here, and that will take you to your preferred destination, whichever section you would like to focus on more. In this electronic properties summary, we will first recognize the differences between metals, semiconductors, and insulators regarding their conductivity. For metals, decreasing the temperature will increase the conductivity because thermal energy increases the amplitude of atomic vibrations, and those vibrations scatter electrons. So by providing less thermal energy, we will have a lower amplitude of atomic vibrations and therefore scatter fewer electrons. Increasing the grain size of metals will also increase the conductivity because electrons are scattered by defects. When you increase the grain size, you are reducing the grain boundary area, therefore you will scatter fewer electrons. When you reduce the cold work, it will increase the conductivity because less cold work means fewer dislocations, and when you have fewer dislocations, fewer electrons will be scattered by those defects. Finally, for metals, a lower level of impurity atoms will increase the conductivity because, again, when you have fewer impurities, those impurities will scatter fewer electrons. For semiconductors, increasing the temperature will increase the conductivity because thermal energy creates electron-hole pairs. Increasing the grain size will increase the conductivity of a semiconductor because, again, grain boundaries scatter electrons. Increasing grain size reduces grain boundary area, therefore scattering fewer electrons. Adding impurity atoms will increase the conductivity because impurity atoms donate electrons or electron holes. This technique is also referred to as doping, which we will get into a little bit more in detail in a little bit. Finally, let's talk about insulators. Insulators, when you increase the temperature, it will increase the conductivity because thermal energy again creates electron-hole pairs. A very important note to remember would be that resistivity is the inverse of conductivity. So whatever increases your conductivity will decrease your resistivity of that material and vice versa. Next, we are going to discuss band structures. For metals, there are two potential band structures. We have band structure 1 with a half-full valence band. So this whole thing is the valence band. There are filled states and there are empty states. In a half-full valence band structure, the electron moves from the filled states to the empty states because the higher energy states are easily accessible for the electron to move. For the second metal band structure, we have an overlapping valence band and conduction band, such that the electron moves from the full valence band to the empty conduction band because those higher energy states are easily accessible to the electron. A good example of a metal that has the half-filled valence band structure would be sodium, where a good example for the overlapping band structure would be magnesium. The reason is that sodium has a half-filled valence band again, so it has 3s1, only one of two electrons are in the valence band. Magnesium has a full valence band because it has 3s2, so your s band is going to be completely full with 2 electrons. The conductivity of these two different types of metals are high. So metals have a high conductivity. So the conductivity of sodium happens to be about 2.1 times 10 to the 7th inverse ohm inverse meter, where the conductivity of magnesium is 2.28 times 10 to the 7th power inverse ohm inverse meter. Continuing with band structures, we are now going to talk about semiconductors and insulators. For semiconductors, we have a full valence band, followed by an energy gap, and then an empty conduction band. Now, at a temperature of absolute zero, the conduction band is empty of electrons. Increasing the temperature provides thermal energy for electrons to jump the energy gap to the valence band, which looks something like this. So the electron jumps from the valence band to the conduction band through thermal energy, leaving behind an electron hole. Generally, the gap size for semiconductors is anywhere from 0.1 to 2 electron volts. For insulators, we also have a full valence band, followed by an energy gap, and then an empty conduction band. At absolute zero, the conduction band is empty of electrons. Increasing the temperature provides thermal energy for electrons to jump into the conduction band, leaving behind an electron hole. The difference would be that an insulator has a much larger gap of about 2 to 6 electron volts. The thermal energy is what causes the electron to jump from the valence band to the conduction band, leaving behind an electron hole. A good example for an intrinsic semiconductor might be silicon. Silicon has an electron volt energy gap of 1.12 with a conductivity of 4 times 10 to the negative 4 inverse ohm inverse meter. A good example for an insulator might be carbon in its diamond form. Carbon has a 5.5 electron volt energy gap and a conductivity of somewhere around 10 to the negative 17th inverse ohm inverse meter. So from those values, it's quite obvious to see that semiconductors have a moderate conductivity, where insulators have a very low conductivity. Next, we're going to be talking about doped semiconductors. To begin, we're going to talk about intrinsic semiconductors. A good example of an intrinsic semiconductor might be group 4, with no impurities. By no impurities, we really mean just having less than 10 to the 21st impurity atoms per meter cubed. A good example of an intrinsic semiconductor might be silicon. Intrinsic semiconductors have the same number of electrons as they do number of electron holes, otherwise known as electron hole pairs. These electron hole pairs are created when an electron jumps from the valence band to the empty conduction band through thermal energy. So by jumping the energy gap, the electron is leaving an electron hole here. P-type semiconductors might have a group 4 element with group 3 impurity atoms. A good example of this type of element might be boron. Your p-type impurity atom will have one less valence electron than your group 4 base element. Because it has one less valence electron, you will have more holes than electrons, otherwise known as majority carriers are electron holes. So this is a p-type, otherwise known as positive carriers. Those are the majority carriers for your conduction. Here in the band structure, we see that the electrons jump from the valence band to the energy level of those p-type dopant atoms. For an n-type semiconductor, we have a group 4 base element with the group 5 impurity atoms. A good example of this might be phosphorus. Now, just like p-type semiconductors have one less valence electron, n-type semiconductors have one more valence electron. As a result, we will have more electrons than holes. Majority carriers are electrons. So this is called n-type, otherwise known as negative carriers. Here in the band structure, we see that the electrons at the energy level of the n-type dopant jump into the conduction band because there is a very small energy difference between these two levels. This concludes our electronic properties summary. Next, we will dive into some example problems. To begin our example problems, we will start off with the multiple choice concept questions. A good strategy when solving these types of questions would be to underline the key terms in the question, and also you must not only explain why an option is a correct answer, but also explain why the incorrect answers are incorrect. So you will see these strategies as we go through each of the example problems. Concept question, example 1. Which of the following terms refer to a group 4 N-type semiconductor? A, donor, is a correct answer because N-type donates electrons to the conduction band. So remember that when you have an N-type semiconductor, the impurity atoms contain one more valence electron than the group 4 element, such that the electrons will be donated to the conduction band. Option B, exhaustion, is also a correct answer because exhaustion will occur when all extra electrons from the impurity atoms are moved to the conduction band. So again, since the impurity atoms have one extra electron, once those electrons are all donated to the conduction band, you will have a state of exhaustion. Option C, electron hole majority carrier, is not a correct answer. The reason would be that N-type is electron majority carrier. Again, you have donated electrons, so the amount of electron carriers is much higher than the hole carriers. Option D, greater conductivity than P-type with the same doping level, is a correct answer because you have the same amount of P-type carriers as you do N-type carriers based off of the same doping level. Now, the mobility of electrons is about twice as large as the mobility of holes, so the N-type is going to have the higher conductivity. Option E, group 3 element impurities, is an incorrect answer because group 3 impurities would be P-type doping. Group 3 element impurities have one less valence electron than group 4 elements. For this question, we have 3 total answers. A, donor, B, exhaustion, D, greater conductivity than P-type with the same doping level are all correct answers. Concept question, example 2. In comparison with intrinsic silicon, a boron-doped silicon wafer has blank. Option A, greater conductivity, is a correct answer because doping increases the conductivity of the intrinsic silicon. So remember that when you add impurity atoms to a semiconductor, it will increase the conductivity. Option B, a larger energy gap, is an incorrect answer because the energy gap does not change with respect to the concentration of impurity atoms or with temperature. The energy gap is dependent upon the host element of the semiconductor, which in this case is the same. The host element is silicon for the intrinsic and for the doped wafer. Option C, D, and E are all kind of related to each other because they're talking about the number of N-type and P-type carriers. Option C has more N-type carriers is an incorrect answer. Option D has more P-type carriers is a correct answer. Option E, equal number of P-type and N-type carriers, is obviously incorrect then. The reason that there are more P-type carriers would be that boron is a group 3 element, which would be a P-type dopant for the group 4 silicon, otherwise known as an electron hole majority carrier. So the boron has one less valence electron than group 4 silicon, therefore contributing electron holes to the semiconductor. For this question, we have 2 answers. Option A, greater conductivity, and option D has more P-type carriers. Concept question, example 3. Which of the following terms refer to semiconductor devices? Option A, bipolar PNP avalanche diode, is an incorrect answer because It's possible to have a bipolar PNP transistor, and it's possible to have an avalanche diode, but not together, though they are two completely separate devices. Option B, solar cell, is a semiconductor device. Option C, rectifier MOSFET, is an incorrect answer because you can have a rectifier, that's a semiconductor device, and you can have a MOSFET, otherwise known as a metal oxide semiconductor field effect transistor, is also a semiconductor device. But together, these two are not a semiconductor device. Dual avalanche diode is an incorrect answer because only avalanche diodes, so again, only like it's called an avalanche diode. A dual avalanche diode is not a semiconductor device. Option E, light emitting diode, is a correct answer. Also known as an LED, so you often see these in traffic stoplights. So they are working semiconductor devices. For this question, we have two answers, option B, solar cell, and option E, light emitting diode. Concept question example 4. Which of the following will increase the electrical conductivity for lead? Lead, of course, is a metal, so that's something that's important to keep in mind as we're answering this question. All right. Option A, increasing temperature, is an incorrect answer because thermal energy will scatter more electrons. So when we increase the temperature, we are providing more thermal energy, and more thermal energy means more electrons will be scattered. Option B, decreasing temperature, is a correct answer because thermal energy, again, scatters electrons. So when we provide less thermal energy, we are going to scatter fewer electrons. Option C, adding a few percent of copper, is an incorrect answer because impurities scatter electrons. So if we provide more impurities, we will scatter more electrons, therefore reducing the conductivity. Option D, increasing the grain size, is a correct answer because increasing the grain size will reduce grain boundaries, which will consequently scatter fewer electrons. Grain boundaries are one of those defects that scatter electrons, so when we have less of them, we scatter fewer electrons. Option E, deforming the metal by cold rolling it, is an incorrect answer because by cold rolling the metal, we increase the amount of dislocations, and dislocations are defects that scatter electrons. So more dislocations will scatter more electrons. For this question, we have two answers. Option B, decreasing temperature, and option D, increasing the grain size. Concept question example 5. If the temperature in the room increases from 20 degrees Celsius to 50 degrees Celsius, conductivity will A, increase in a metal like magnesium, is an incorrect answer because increasing the thermal energy scatters more electrons, for metals at least. Option B, increase in a doped semiconductor like N-type silicon, is an incorrect answer because thermal energy does not much affect doped semiconductors, only intrinsic. Option C, increase in an intrinsic semiconductor like germanium, is a correct answer because increasing the thermal energy creates more electron-hole pairs in the semiconductor, again, only for when they're intrinsic semiconductors. Option D, decrease in a metal like copper, is a correct answer because increasing thermal energy scatters more electrons, and because more electrons are scattered, the conductivity has decreased. Option E, decrease in a semiconductor like silicon, is an incorrect answer because increasing thermal energy means more electron-hole pairs are created. So the conductivity should have increased, not decreased. For this question, we have two correct answers. Option C, increase in an intrinsic semiconductor like germanium, and option D, decrease in a metal like copper. Calculations example 6. If an intrinsic semiconductor, energy gap of 0.67 electron volts, has a conductivity of 100 inverse ohm inverse meter at 100 degrees Celsius, what is the intrinsic carrier concentration if the mobilities are mobility of electrons 0.4 meters squared per volt second and mobility of holes 0.2 meters squared per volt second? The equation for the conductivity of an intrinsic semiconductor is given by the conductivity is equal to the intrinsic carrier concentration times the charge of an electron multiplied by the mobility of electrons plus the mobility of holes. Because we're interested in solving for the intrinsic carrier concentration, we're going to solve for that variable. So the intrinsic carrier concentration is going to be equal to the conductivity divided by the charge of an electron multiplied by the mobility of electrons plus the mobility of holes. Finally, we're going to plug in all of the information provided by the question. The conductivity was said to be 100 inverse ohm inverse meter. The charge of an electron is a constant. The mobility of the electron was provided to be 0.4, and the mobility of the hole 0.2. When we calculate our final answer, you should get about 1.04 times 10 to the 21st atoms per meter cubed. So this is going to be our final answer. Calculations example 7. What is the conductivity of a semiconductor if p-type dopant is added to achieve a concentration of 3.13 times 10 to the 21st atoms per meter cubed? We have a mobility of electrons of 0.4 and a mobility of holes of 0.2. Now, the first thing that's important to recognize about this problem is that p-type dopants have majority carrier electron holes. Therefore, the equation we're going to use would be that the conductivity is approximately equal to the p-type carrier concentration times the charge of an electron multiplied by the mobility of holes. So we're going to insert the information that was provided by the question. We have a p-type concentration of 3.13 times 10 to the 21st atoms per meter cubed, multiplied by the charge of an electron, which is a constant, multiplied by 0.2 meters squared per volt second for the mobility of the holes. When you calculate this out, you will get about 100.2 inverse ohm inverse meter for the conductivity of this p-type semiconductor, which is our final answer. Calculations example 8. How many grams of boron are required to achieve a concentration of 3.13 times 10 to the 21st power atoms per meter cubed when added to a 1 meter cubed semiconductor material? To solve this problem, we're going to use some dimensional analysis. So if we're looking for the number of grams, we need to know the number of atoms of boron that we are adding to the semiconductor material. Conveniently enough, we are looking for 3.13 times 10 to the 21st atoms per meter cubed, and we are adding to 1 meter cubed of semiconductor material. So the number of atoms is just going to be 3.13 times 10 to the 21st power. We will multiply this by 1 mole divided by Avogadro's number, the number of atoms in a mole, and then multiply that by the atomic weight of boron for 1 mole. So as you can see, the units are going to cancel out such that we are left with grams. When we insert all the information in, we will see that again we have 3.13 times 10 to the 21st atoms multiplied by 1 mole divided by 6.02 times 10 to the 23rd atoms, Avogadro's number, multiplied by 10.81 grams per 1 mole of boron. So again, this is a constant. It can be located on your periodic table, or in this case it was given to you as a constant listed above. When we calculate our final answer, we should get about 0.056 grams of boron. This is our final answer. Band structures, example 9. Draw the band structure for a metal like potassium, valence equals potassium plus 1 when ionized, and a semiconductor like silicon, and briefly explain the reason for differences in conductivity for each type of material. Let's talk about potassium. So it tells you that potassium is +1 when ionized, meaning that it is in group 1 of the periodic table. So its band structure is going to have a half-full valence band because it only has one of the 2 electrons in the S shell. When you have the half-full valence band structure, the electrons move easily from the full states to the empty states because the higher energy states here are easily accessible. Now, for a semiconductor like silicon, we have a filled valence band followed by an energy gap and then an empty conduction band, such that thermal energy creates limited electron-hole pairs. The electron will jump the gap with this thermal energy, leaving behind an electron hole. For semiconductors, only a very small fraction of atoms contribute their valence electrons as charge carriers, while for metals, all valence electrons are contributed as charge carriers. For these reasons, metals have a high conductivity, while semiconductors have a medium conductivity because they are limited by thermal energy. Band structures example 10. Using the band gap diagram schematics shown below, show and draw the charge carriers for intrinsic silicon and boron-doped silicon semiconductors. For intrinsic silicon, the charge carriers are both electron holes and electrons, and you have an equal number of each because an electron hole is created when an electron jumps the energy gap into the conduction band. For boron-doped silicon, boron is group 3 of the periodic table, and silicon is group 4. So this is a p-type semiconductor. So we have the energy level of the p-type impurities here, and the electrons are going to jump into this energy level from the valence band, leaving behind electron holes. So these are the charge carriers for the p-type semiconductor, which is boron-doped silicon in this case. We're going to end the screencast with a test review wrap-up. At the beginning of the screencast, we covered a summary of electronic properties concepts, talking about the differences between metals, semiconductors, and insulators regarding their conductivity. Then we went into a multiple choice test example concept problem section, where we discussed different strategies for tackling multiple choice questions for electronic properties questions. Then we discussed calculation test example problems. We talked about how you can identify the correct equation and then rewrite it for what you need to solve for, and then finish with plugging in the given information from the question. At the end of our screencast, we went over band structure schematic test example problems. We talked about how we can use the band structures for different materials to explain their differences in conductivity. I hope this screencast was helpful. Thank you for watching.